All right, so we do have recording started. All right. So last time we talked about a SR latch, and the truth table of the SR latch looks like this. And you got a chance to go through the PDNC table, to kind of study or understand why an SR latch behaves the way that it does. Okay. So are we remembering what NC represents in this truth table? Because there are two terms that are both abbreviated to NC. What is this one? No change. That is correct. Okay, very good. Because if you just read a little bit ahead, explains this is no change, right? And that is exactly why the SR latch is the simplest memory device, okay? Simply because when you transition to either 0, 1 or 1, 0 to 1, 1, it just remembers the previous state. So 1, 1 as input, if S is 1, R is also 1, you're simply telling the SR latch, whatever it was before, just keep that, okay? The only thing you cannot do is to transition from 0, 0 to 1, 1 directly, okay? Because I demonstrated what happens when you transition 0, 0 to 1, 1 in the class before the exam. So what happened? It freaked out. Okay, yes. I suppose you can say that. So what happens when people freak out? They throw themselves into a loop. Yes, and that works for SR latches too. It threw itself into a loop. Okay. So depending on whether you like, MBTI or Myers-Briggs type indicator, psychology, personality type kind of thing. So depending on your personality, the type of loop you can throw yourself into is different. So since I'm an INTP, I throw myself into a loop that is commonly called the TISI loop. Okay, but since this is not a psychology class, I'm not gonna go too deep into that. But since you said the SR lectures kind of freak out and it got into a loop. Okay, so that's the SR latch. Okay, so from an SR latch, so today I'm not going to go through every single intermediate version like in detail, but I will still kind of go through that a little bit. So the next thing is called a D flip flop. The D flip flop is also known as a level sensitive D flip flop. What it does is it has an um, actually yes, it is a level sensitive D flip flop. And the way it works is there's an enable. So let's go ahead and actually construct the circuit because I think it helps if you can see how I construct the circuit, and then you can actually see how it works. It looks like a big mess, right? If you look at the text description here, but it is relying on SR latch as a component. So it really has one, two, three, four, um, only has four components because the other four are output pins and input pins. So we'll go ahead and construct this circuit here, okay? And what I'll do is I'm going to decrease the font size just so that I can kind of keep this portion in display when I'm constructing the circuit. Same trick that I did last time, except this one is a little bit more wordy. And then I'll go ahead and start up Logisim, and then we'll go from there. Okay, yeah, this is fine, and I just need to run Logisim. There we go. All right, so we need to go back to take a look at the diagram, okay, and make it always on top, at least for the time being. All right, so what do we need? There's a NOT gate N. There are two NAND gates. One is N1, one is N2. There's a SR latch which I need to construct. There are input pins D and EN, and there are output pins Q and NQ. So we're gonna throw this thing together. I need to construct the SR latch first, okay? So that should be pretty quick now, right? Because we already have seen an SR latch. So we just have to construct the SR latch pretty quickly, like so. And then just go for narrow, make an extra one, like so. And then the SR latch has two input pins. Here's one, And here's the other one, like so. So what I'm doing is I'm actually constructing the circuit kind of from scratch. Okay, so I'm not pulling an SR latch directly from the library. Actually, there's an SR latch in the library, but it doesn't work the way that I want it to work. So that's why I'm constructing my own SR latch because this is a NAND gate based SR latch. You can also construct the SR latch using NOR gates. So the one that is included in the library is a NOR gate type SR latch, and the one that I'm constructing here is a NAND gate based SR latch. They can get the job done. Both of them can get the job done. It's just that the way they get the job done is slightly different. Okay, so now we have a SR latch. So I create a circuit, and I just have to change its name. Okay, so the way you change the name of the circuit is simply to go to click anywhere, okay, other than the component, and then you can see that now it is selecting the entire circuit. And then you can go change the circuit name. We'll call this the SR latch. There we go. And that's it. Okay. And now I can go to project and add another circuit, okay, which is the one that I intend to make. So that's a D flip-flop. I'm just going to use DFF for D flip-flop. So now I can create this circuit over here. I need a NOT gate. I need two NAND gates. So I need to go back to gates over here, go to NAND. Okay, just kind of go through the same changes that I did before. Like so, and there are two of them. I will name the components later, and I also need the SR latch. So the SR latch that I have constructed is now basically my own class, which means I can now go to, oh, it's on the top, sorry. There we go. So now we go to SR latch, and the SR latch that I constructed earlier is now a component I can reuse. This should be nothing new, okay, because you already did something like this I think in week 1 or 2, when you use the NAND gate to create a NOT gate, and I believe the other one was an AND gate. Okay, so you kind of know how to do some of this already. So it's good to name the components. Okay, this is our SR latch, and the label is SR. This is the NOT gate, okay, which is just negation. I'll label it as N. This is NAND gate N1. So I'm naming all the components the same way as they are named in the text version. So this is N2, like so. And now I need some input pins and some output pins. This input pin, I will just name that D. And I will need another input pin. I'll name this one EN for enable. I need two output pins. One output pin is going to be named Q, and then the other one is NQ. So there we go. And this one is just NQ, like so. All right, so I have all the components. And now what I need to do is simply to make all the connections. So this is going to look a little bit busy, okay? So we can see how D is going to the first input of N1. So I'm going to move things around just a little bit so that everything aligns a little bit better. It also goes to N dot in, okay? So this is the NOT gate, and we want to connect it over here. So it goes here, and then it also goes here. So that would be the first node. I'm just double checking. The port on the D input pin connects to the first input of N1. It also connects to the only input pin of N. So I got that part done. Now we move on to the second line. The second line says EN goes to the second input of N1. Okay, that may take some creative drawing, but I can get it. Okay, there we go. But it also goes to the first input of N2. Okay, so now I just kind of move N2 to here. I mean, I just like things to be more or less aligned. Okay, so that's N2 right there. And then the output of N, which is the NOT gate, goes to the second input of N2. Oh, okay, I just made a mistake, sorry. That was that was me. Okay, because this is supposed to go to the first input of N2. There we go. Sorry about that. And this one goes to the second input of N2. So just have to. It just looks a little ugly. There we go. Okay, so that's that. And now we look at the N1's output. It goes to SR.S. Okay, so now we have to kind of move this one a little over a little bit here. This is the S. I should have labeled the pins. It's okay. I mean, I remember the top one is S, and then the bottom one is R, which is going to take the output of N2, and it connects here like so. And then the output pin Q goes to Q dot in. So that means the output pin that is labeled Q, which is supposed to be this one. I think I forgot to type enter after the Q. There we go. So this is output pin Q. Come on. There we go. All right. So this one is NQ. It goes to the NQ pin of the SR latch. Okay. Question? Well, I'm gonna show you. All right, so the first thing is we notice that the SR latch is outputting quote unquote error, but it's not actually error. It is simply saying, I don't know what I'm supposed to output. Why? Because the two inputs of the SR latch are both ones. So if you remember the truth table that we just looked at, what does it mean when both inputs of the SR latch are both ones? No change, right? No change from what? I did not initialize the SR latch to begin with. So that's why it's a quote unquote error because it doesn't know what it is supposed to be. Okay. So if you, oh, okay, this one is supposed to be EN. Let me make sure that it is labeled properly. Okay. So go here and then just make sure that we are labeling everything. Okay, there we go. It's all good. So what this circuit does is it is a enabled or otherwise known as level sensitive. So enabled and level sensitive are basically meaning the same thing. It simply says if enable is a 0, then the SR latch is not going to change its state no matter what you do with the D pin. And D stands for data, okay? So the input pin D or data is what you want the circuit to remember, meaning that D should be the same as Q, and then NQ should be the opposite of D. EN is enabled. So when EN is a 0, the circuit, the entire device is quote unquote disabled, which means it doesn't do anything no matter what you do with the D pin. When the circuit is enabled, which means when EN is a 1, then the Q pin will follow the D pin. Whatever state you change the D pin to, the Q pin will be changed accordingly, as long as the EN pin is a 1. Okay, so that's the behavior. I can demonstrate. So right now EN is a 0, and I can change the D pin all I want, and you can see how the SR latch does not change at all. Okay, and that's why the EN pin has its name because it's enabled. But the moment I change EN from a 0 to a 1, the the output of the SR latch, the Q pin is now following the D pin. If I change the D pin, the Q pin changes as well, just like that. But the moment I disable the enable, I can now change the D pin all I want, and nothing happens to the Q pin. So this is called a D flip-flop. The D stands for data, but it's called a flip-flop instead of a latch. Okay, and it is one of the simplest, easiest to understand memory device because you have only one single control input of saying should I remember, should I echo or not, and then you have the content to be echoed by the circuit itself. The moment you turn off the enable, no matter what you do with the D pin, the output would stay exactly the same. Are we good so far with this circuit? So If I were you, I would basically apply what we have learned in the NCPD analysis and just repeat the whole thing, okay, of all the changes that I did by hand. Well, not the whole thing, but a few, at least a few of those pin change transitions, so that you understand how to track down the NCPD for a D flip-flop like this, because that technique works here as well. Yes. Yeah, so as long as En is a 1, Q will eventually mirror whatever D is. So there are definitely some propagational delay in between, but it will follow. So I can do this one more time. When En is false, and then whatever you do with D doesn't really change anything for the output. But the moment you turn it on, then whenever D changes, Q will change quickly shortly after. And then if you change D back, Q would also change quickly shortly after. All right, so this is what we call a level sensitive D flip flop. The analysis of the circuit is actually in the notes too. Um, it, it's a whole lot of text, to analyze it, but it is there. The next circuit is called the edge sensitive D flip flop. It is a little bit more complicated because we can see that, well, okay, it has two SR latches and it basically has three SR latches because NAND 3, which is a three input NAND gate, combined with NAND 2, the N1 and N2, actually makes a SR latch by itself. But on one side, it has three input. And then we have pretty much the same, the usual suspect, data input, Q as an output. We don't even bother with NQ this time because most of the time NQ is not really useful if you're not using an SR latch. But this time, instead of EN, we have another input pin called CLK, which stands for clock. Okay, so this particular circuit behaves in a slightly different way. Okay, so we'll go ahead and construct this circuit too. Let me get rid of the other one first, and then we'll go ahead and construct this one. So this is also something that you can do on your own, which I highly recommend because the moment you do this and then you try to explain what is happening, why the circuit works, how the way it works, the moment you go through the NCPD analysis on something like this, you gain a much better understanding of how this stuff works. Okay, what type of occupation, what type of people actually really look into this sort of thing day in and day out? We know those are not software engineers. So what kind of people study the inner workings of a processor? So you guys can try to answer that question when I'm recreating a circuit. Hmm? Embedded system engineers typically work with larger components instead of gate level components, but you're close. So I call this one EDFF, or edge sensitive D flip flop. So the answer is computer engineers. Okay, so as opposed to software engineers, computer engineers focus more on how the inside of a processor works. Um, I cannot say in general computer engineers are in great demand, but certain types of computer engineers are indeed in great demand. So what do you think OpenAI is doing that has a demand on computer engineers? What is the worst nightmare of OpenAI, the basically the publisher of ChatGPT? I'll let you guys think about that a little bit. Okay. I'll give you a clue. It has something to do with Jensen Huang. So now you have to ask yourselves, who's Jensen Huang? What does he do? Or which company is he associated with? And why would that have anything to do with OpenAI? Okay, so do we have any answers? Who's Jensen Huang? He is the CEO of NVIDIA. Yes. So how does NVIDIA and OpenAI relate? Yep. So in order for OpenAI to run its data centers, right, in order to run all the AI stuff, it needs the NVIDIA chips. So are the NVIDIA chips in great demand? They are indeed in great demand. So what if NVIDIA, what if Jensen Huang goes like, hey, I got so many people who really wants my chip. I really cannot sell, you know, the quantity that you want me to sell to you. I am sorry. Okay. That is the worst nightmare of OpenAI. So what do you think that nightmare has to do with computer engineers? If you were OpenAI, what would you do? You are being held hostage by NVIDIA, not so much that they want to hold you hostage, but simply because they cannot respond to all the demands of everybody who wants, the chip that they are manufacturing. So what do you do? Create your Yep, exactly. You create your own. So that's what OpenAI is trying to do. Is they're trying to create their own chip to perform all the calculations. I believe there are multiple companies who are on the same path because they find out that hey, instead of paying a lot of money for Nvidia to sell the chip, I can probably make it myself for a whole lot less. So that's kind of interesting because on paper, computer engineers are not doing so well in terms of employment. But in terms of people who can indeed help these companies design their own chip for AI purposes, there are jobs out there. Okay, so I just want to point that out. All right, so I just made all the components here. Now we have to make the connections between the components. So this is the really kind of you know so I think this circuit works better if I reposition the pins like this. Okay. All right, so the data pin goes to the second input of N2. So we'll kind of hook up these two over here. So that's the first node right there. There is one node. The second node goes from the clock pin. Oh, it's not EN, it is clock. Okay, that's my mistake. So it's a clock pin this time. It goes to S dot R. It also goes to N1 dot in one, which is the middle one. Okay, so we'll go ahead and put this over here. I might need to decrease the zoom a little bit. And then the SR latch is over here. And we wanted to connect to the R one, okay, which is the one at the bottom. Okay, all right, cool. I will probably regret the way I put the components. It's okay. I'm gonna, I will kick the can down the road. All right, so there we go. We got the second node done. The third node connects the output of N2, which is this terminal, to the second input to the last input of N1. Okay, I can still do it. So there we go. And it also needs to connect, wait, this one, right. So it connects, also connects to S.S, which is, ooh, okay, I made a mistake earlier. This is S.S. Oh, okay. This is S.R, and then this one is supposed to connect to S.S. There we go. All right. And one's output is supposed to go to N2 in 0. So it's supposed to go here. And you guys might think, huh, you're out of ways to route it. Yeah, I can route it all the way around. There we go. And it's supposed to go to C.R. This is C. And then C dot R is the one at the bottom. Okay, so that's C dot R. And S dot NQ, which is this guy, is supposed to go to C dot S and also N1 dot in 0. Okay, we can do that. Just barely, but I can do it. I can do it. And then it's supposed to go to in 0 of N2. Okay, I'm lost. And one's output goes to N2 in 0 and C dot R. Okay, I think I misread two lines. I think I confused myself with these two lines, so it's time to go double check these two. N2's output is supposed to go to N1, the last input of N1, so I got that. It's supposed to go to S dot S. So this one goes to S dot S. So that's done correctly. N1's output, which is this one, connects to the first input of N2. I got that. It is supposed to also go to um, C dot R, which is the bottom here. Okay, so that one is incorrect. Okay, so I have to fix that. Okay, there we go. All right, and then we have S dot NQ going to the first input. Okay, so this is NQ from S, um, and it's supposed to go to the first input of N1, like so. Yes. Okay, excellent. And finally, C dot Q, which is this one here, goes to the Q pin. All right. Okay. So kind of complicated, right? So what I do now, okay, if you record, if you look at watch the recording of this video, you should be able to perform an NCQD, um, PD, sorry, NC no connectivity, and then PD propagational delay analysis of the circuit of the changes that I'm going to make. Okay, so I can describe it first, and then we'll do it. This particular circuit, instead of an enable, has a clock. So the Q pin is supposed to mirror the data pin. Okay, as usual. The question is, when does it do that? Okay, and the answer is when clock has a rising edge. In other words, at the very moment that the clock pin goes from 0 to 1, that is the moment when the state of the data pin should be copied to the state of the Q pin. So it is about timing, okay, this time. So we'll go ahead and test it, okay? Since the clock pin is not moving, it's not changing at all, we'll go ahead and just kind of cycle through the data pin and make sure that nothing happens to the Q pin. Okay, kind of as expected, cool. So we'll change it to a 1. The clock pin is now a 0. If I click it again, it becomes a 1. The transition from a 0 to a 1 is called a rising edge, okay? So this circuit is supposed to be sensitive to a rising edge. At the moment that you have a rising edge, whatever the data pin has at that point should be copied to the Q pin. That is the expected behavior of an edge sensitive D flip flop. So I'm going to change the clock pin right now from a 0 to a 1 and see if the Q pin is going to follow exactly that. See if it's going to copy the data pin. Aha, cool, right? So now the question is, well, the other circuit would do this too, because when the enable pin goes from 0 to 1, then the Q pin is going to follow the data pin as long as the enable is a 1. But for this one, because it's only sensitive to the moment that the clock pin transitions from 0 to a 1, so that means at this point of time, I should be able to change the data pin back to 0, and nothing should happen to the Q pin, okay? Because it is supposed to be edge sensitive and not level sensitive. So we'll test that out. So now we go back and we change the data pin from a 1 back to 0. Aha! Nothing happens to the Q pin because there's no transition, there's no rising edge with the clock pin. Okay, so now we go like, okay, what if we have a falling edge instead of a rising edge? Okay, a falling edge means the clock pin goes from 1 to a 0. And I can tell you the circuit is not supposed to change the output Q pin on the falling edge. Okay, so we'll double check. Aha, okay, nothing happens to the Q pin, all good. On the other hand, if I click the clock pin again, it will be another rising edge. So at that moment, the data pin, which is now a 0, should be copied to the Q pin, which is currently still a 1. Does that make sense? Okay, so we'll give that a try. Aha, that works exactly the way as I described. So this is called an edge sensitive D flip-flop. So now the question is, why do we need one way and the other way? Okay, one is, the previous one, the level sensitive D flip-flop, allows me to select which D flip-flop should change. In other words, I have control over the enable of multiple D flip-flop when the data pin is connected together. But by changing, by selecting which D flip-flop is enabled, I can now say, hey, of the entire collection of D flip-flops, only one D flip-flop is supposed to change according to the data pin. It controls which. Okay. On the other hand, this circuit here, which is also called an edge sensitive or clocked D flip-flop, controls the timing. So it controls the timing of when it should update. So you might think, well, isn't it kind of both important? Like which D flip-flop should change and when it should change? Then you'll be correct. Okay, I need both. So the next circuit combines both of these elements. And we're getting to something that is complicated enough that I don't want to. I just give you the diagram because the text description is just a little bit too much. But you can see in this case, we have a data input pin, an enable, and also a clock. So in order for the output, which is still called a Q pin, in order for the output to change, this time you need enable to be a 1, and you also need at the same time that the clock pin is having a transition from a 0 to a 1. When both of those conditions are met, then whatever the data pin has, a 0 or 1, is going to be copied to the Q pin. Are we okay so far with this? So I'm not going to build a circuit because it's going to take a little bit of time. But that's the behavior of this circuit. It is the combination of a level sensitive and a edge sensitive D flip flop. So at this point, I can tell you, you know, um, how many people have seen the performance of an orchestra, like a symphonic, orchestra. Okay, so there's usually a conductor, right? So the conductor, and there are many instrument groups. When the conductor is flicking, the baton, I think it's called a baton, okay? That's controlling timing, okay? It's like, with a 3/4, time signature, is 1, 2, 3, 1, 2, 3, works really well with waltz, type of music. Or you can have like a 4/4 kind of time signature, 1, 2, 3, 4, 1, 2, 3, 4, and so on, okay? So each time, the baton is flicked, it is a transition, okay? But sometimes the conductor will stare at one section of the musical groups. It's like, okay, you guys are way too loud. Okay, typically that's the piccolo because piccolo really stands out. In any orchestra, you need one guy playing the piccolo, and then you have like 20 people playing the flute trying to compete with piccolo, and they will still lose. Do you guys know what is a piccolo? No. Think of a flute, except it's a lot smaller. So the frequency is a lot higher and it stands out a lot. Or you can think about trumpets. Okay, you only need like two trumpets to counter 20 flutes. So even though both are you have to blow air into it, the efficiency of a flute is really low because half the air is actually blowing over the instrument. But when you look at a trumpet, it's all going through the instrument. So anyway, this is not a music class. So I'm not going to go too far into explaining musical instruments. But the conductor needs to address two things. One is which musical instrument group do I need to divert my attention? Okay. And the second one is I also need to keep the beat, okay, the rhythm for the entire group. Okay. So enable is basically is the conductor staring at me? The clock is the baton of the conductor. Okay. One controls the timing, the other one says, are you addressing me? You know, so you need both in order to update. Okay. You need to say, okay, the conductor is looking at me and, the baton is moving. So I have to play the next note or something along that line. So with this, you would think we got everything, right? Nope. We have one more thing, one last detail. Okay. So now we have 4 pins. We have the 3 pins as before. Okay, we have the data pin, which is the incoming data, what I'm supposed to remember. We have the enable. We are asking, am I supposed to update? Because of all the D flip-flops, am I the one supposed to update? And then we have the clock pin, which is saying, when am I supposed to update? Because you only update when the clock pin is going from a 0 to a 1. So what is the last pin going to do? It's called the reset pin. So when you look at the reset pin, and the two logic gates that connect to the reset pin, then you ask, what does it do? Okay, if the reset pin is a 0, what does it do to both of these gates? Let's take a look. So if the reset pin is a 0, then A3 is guaranteed to output what? 0. Okay, so that means R is guaranteed to be a 0. What about O1, which is OR1? Okay, now this is an OR gate, but this is a negation. So that means when reset is a 0, it is first negated into a 1 before becoming the input of before becoming the second input of O1. So what does it do to the output of the OR gate? It's guaranteed a 1, right? So that means, oh, okay. So if the reset pin is a 0, the last SR latch, which is SRC, is guaranteed to see a uh, 1 for the S pin and a 0 for the R pin. And what does that do to an SR latch? According to the truth table, what happens to the Q pin of the SR latch? It becomes a 0. Very good. That is why it's called a reset pin. Because when the reset pin is a 0, it guarantees to change the output to a 0, regardless of what the rest of the circuit wants to do. Is that okay? It is a reset. Okay. Why do we need a reset pin? What happens when the computer starts up, or your phone or your fitness watch, whatever? Okay. Whatever thing that you have a processor in, okay, when you first power up, what's going to happen to all the logic gates and whatnot, all the D flip flops and all the SR latches? When they wake up, they're in some unknown state. Okay, so do you want your device to just start execution at some random location, which turns out to have some random content? Probably not a good idea. Okay, so you probably want to say, well, when the computer starts up, we want to start at location 0, and all of these other registers also will be filled with zeros. Okay, or some kind of known state. Does that make sense to you? Okay. And that's why there's a global reset line on just about any computer. When you first start up your computer, that reset line is quote unquote asserted, okay, which basically means it's telling every single component in your computer and say, reset yourself, reset yourself, reset yourself. Yes. So it depends on what kind of reset you're doing. There's a hard reset and there's a soft reset. Um, if you do the hard reset, which is equivalent to unplugging the computer, plugging it back in and turning it back on, then everything should be reset. When you do a soft reset without cycling power first, that may or may not trigger all the devices to actually reset. And that's why, with faulty devices, sometimes it makes a difference. You can do a control alt delete, or you can just ask the computer to reboot, and somehow the component, sometimes it's a Wi-Fi component that wasn't working, continues not to be working. You have to actually power down the whole thing and then power it back up, and then miraculously everything works again. It's much harder these days with laptop computers, because Microsoft Windows by default would only do a quote unquote soft reset. Even when you hit the power button, it's not a hard reset. I cannot remember exactly what you need to do to do an actual hard reset, but you have to do something to do a hard reset because the soft reset is a lot faster. So unfortunately, sometimes you have to do that, with certain types of problems, but it is not possible with a cell phone. Well, not on most cell phones, because on most cell phones you can't really easily disassemble it to the point to disconnect the battery. Most of the things are glued inside the cell phone, so it's not like, you just need some fancy screwdriver to open it up. You need cards to kind of help to separate the glue from, you know that's gluing all the components together, and hope that in the process you're not cracking the screen. Don't ask me how I know these things. Yep. It is a science. It's an art, by itself, to repair modern day cell phones. And most computers are going in that direction too. Things are being glued instead of, being held together by screws. And that's one reason why I choose, this particular Lenovo computer is it is still using screws. So I can actually change the components inside, especially the SSD drive, which is guaranteed to fail at some point. So, all right. So anyway, this is called a resettable, level sensitive, and edge sensitive D flip flop. Okay, so that's kind of its full name. Okay, so this is great. Okay, so now we have a device that can remember 1 bit. Okay, which is not really helpful, right? One single bit is not going to do a whole lot of good. So what if you want to remember 8 bits, okay, which is called a byte? Well, the way we do it is simply to bundle a bunch of them together. So this thing is called a register. We call this an 8-bit register, but you can see that each component, each one of these rectangle boxes is really the circuit that we were looking at before. Okay, so we are really just tiling 8 of these things together, connect the pins in a certain way, and call it a slightly different name. We call this a register. So let's check out, how the reset pins are connected. There's one single reset pin coming in, but that reset pin is multi-dropped to the reset of each individual component. So the reset of every single individual component connect to what we call the same bus. Okay. So when I refer to the term of quote unquote a bus, it means it is using some kind of multi-drop topology, which means it is being tapped into multiple components at the same time. Okay, so the reset bus is multi-dropped into each one of these components. What about enable? Same deal, okay? The enable is on this wire, and you can see it is multi-dropped into all the enables of the individual components. The clock is the same way. Okay, so the clock is the top pin, which is on this wire, and you can see it is multi-drop to the clock of every single component. So what is not multi-drop? The D pin is not multi-drop. So when you look at the D pin, it is an 8-bit D data pin coming in. It goes through a splitter. The splitter splits the 8-bit input into 1-bit outputs. Bit 0 only goes to the top D flip-flop. Bit 1 only goes to the second. Bit 2 only goes to the third one, and so on. So each uh, D flip-flop is only responsible to respond to one of the bits of the 8-bit data input pin in this case. What about the output? Well, each D flip-flop only has one single output, which is the Q pin. So they are all going into a reverse splitter, a merger, okay? And then the output of the merger becomes the actual 8-bit output. In other words, you're basically looking at the same kind of circuit that we were analyzing just a few minutes ago, except this one is handling 8-bit at a time instead of 1-bit at a time. Are we okay so far with understanding what a register is? At least conceptually, okay? I'm pretty sure in implementation, it is not like this because this is not efficient. So I think in terms of implementation, they reuse certain circuits because they're actually common to all of the subcircuit. But conceptually, this is what a register really is, okay? It is just a whole bunch of D flip-flops tied together. All right, are we good so far? Okay. So a register is super important because inside the processor, not counting the RAM, okay, inside the processor, this is the device that can store information and then you can use it to retrieve information. So register is basically one of the most essential or most important components inside the processor. Okay. Do we have any questions about the concept of a register or the underlying D flip-flops? Yes. Say that again. So would this be no, not the cache. So cache memory is a different thing. So cache memory is also known as associative memory. Um, the way you retrieve a piece of memory from cache is by the address. So it's kind of like a hash table, if you know what a hash table is. So if you go to CISP 430, they talk about a hash table. So associative memory is kind of like a hash table. Basically, it is a lookup table. Um, so the processor wants to go to a certain location. I am speaking a little bit ahead of time, okay, ahead of the schedule. So it wants to look up memory. The reason why we need cache is because it takes a lot of time to get to the actual memory. I can give you an analogy, okay? So let's say I'm the ALU, the arithmetic and logic unit inside the processor, the core of the processor that actually performs the addition, the subtraction, the comparison, and stuff like that. So I'm the ALU. What is a register, in this analogy? Well, it'll be a piece of paper that I can just reach my hand and start to jot down stuff, right? Okay, so one register may hold one of the numbers, and then the other register may hold a second number, and I'm supposed to perform addition. I look at those two numbers, perform the calculation, and then use one of the paper to remember the result or basically the sum. Okay, so pretty easy to access. Okay, so using this analogy, how far do you think memory is? So you might think, oh, okay, memory may be something that one of the notebook that you guys are holding is the actual memory. Nope. Go a little bit further. Let's try the library. That is how far memory is. So if I need to go to memory, okay, if I need to say, okay, I just perform an addition, I'm supposed to store the result of the memory all the way to the library. And then in the next instruction, I have to go back to the library, retrieve that piece of paper so I can continue with the calculation. That is not going to be very efficient, right? So what cache is there's a stack of paper outside of this classroom. And every time, I ask someone to remember something, you put something into the library, that person would go like, okay, text says, page 27 is supposed to have this number 45. Okay. That person will first drop a note right outside of the classroom. The last update to location 27 is it has this value. And then run to the library, actually complete the whole transaction. Okay. So if I need to access page 27 again, that person would now go right outside of the classroom, flip through that little stack of paper and say, did Tech just say something about page 27 recently? Oh, yeah, he did. Page 27 should have this content. So instead of having to go all the way to the library, that person just has to go right outside of the classroom and then come back with the answer. That's what a cache is. Then you guys go like, well, how come we don't put all the memory, into this little stash of cards outside of the classroom? Because it is expensive in terms of silicon. The library has multiple floors, okay, to store rows and rows and rows of books. You only have a small table outside of this classroom that can handle like a few stacks of paper. So that's why you cannot use the cache to replace full memory because the full memory is a lot more massive in terms of its capacity. But if I write the code right, okay, I should not have to access the entirety of the library all the time. I'll be accessing a few pages of a few books most of the time. So by caching, by keeping a local copy right outside of the classroom, I can now speed up the operation, tremendously. But nothing is faster than a register because what I'm holding right now is the register. I don't even need to go outside of the classroom, which is most of the time, the boundary of the actual processor core itself. So does that kind of explain, the concept of a cache versus memory and register? Okay. Yep. Hmm? Yes, there are very few of them. Okay, there are very few of them. So with the x86 processor, I think you have 16 registers. 16, as in 1 6 registers. Okay, maybe 32. Okay, it's in the order of something like that. Okay, 16 or 32. Cache memory will be in megabytes. Okay, so you have quite a bit of cache. But in terms of memory space, 32 gigs of RAM. I mean, if you want to run your own LLM on one of those, what, Apple Studio, Mac Studio, right? Yeah, those can go up to what 128 or even more gigabytes of RAM. I wish I have enough money to afford one because then I can run my local LLM instead of having to pay $20 a month. So, but you can see how the trade-off doesn't make sense in terms of money. I think a uh, 64 gig memory Mac Studio is about $6,000 or 326. Okay, doesn't matter. Okay, let's say $3,000. Okay, and it can run a small model. Okay, because 64 gigs of RAM doesn't let you run a large model. It would be kind of like a medium high, but definitely not one of the more complex models. Okay, and then you have to divide $3,000 by 20 because that would be the number of months that you can run, Gemini or ChatGPT or Claude. So 3,000 divided by 20 is what? 150, I believe. Okay. It's 150 not days, but months. So 150 months is how many years? It's, let's see, 150 divided by 12 is it's about 12 years or so. Okay. So you go like, well, that's okay. You just have to run this thing, for 12 months and then you recap all the money that you spent. No, because you have to remember, I still have to pay my electricity. And how quickly do things evolve in semiconductor according to Moore's law? It's doubling every. So the original Moore's law says doubling every 18 months. I think they have revised it to doubling every 24 months. So every 2 years, okay, for the same money, you can buy twice of everything. RAM, mass store, processor speed, blah, 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 and so on. So do you think I want to hang on to that $3,000 computer for 12 years? No. So it does not make sense to buy my own computer to run my own model in terms of, from the money perspective. But on the other hand, if I'm an operative, you're trying to, you know, infiltrate a government, I probably need to do that instead of using ChatGPT. Have you guys read the news lately? They OpenAI caught operatives of a certain country that I know, but I won't name, of submitting queries to ChatGPT about how to control dissidents from that country. It's like, anyway, you can look up that news, okay? I can only tell you this much, okay? But it was just fascinating to read that piece of news. It's like, and by the way, that particular country, the country that runs these ops, okay, is also well known to have their own LLMs, which they copy from yet another country, which I will also not name. So the whole thing is really quite fascinating to me. All right. So besides registers, we also have other things inside the processor. Okay. So let me show you the schematic of the processor that you'll be using for this class. So let me see, open recently. Okay, here. So you go like, that doesn't look too bad until you zoom out. Do, 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 do. Okay, so this is the processor that you'll be using for the rest of the semester. Okay, you'll be translating C code into assembly code and run it in this little processor. Okay, it looks awfully complicated. Okay, lots of wires flying everywhere. But when you look at the individual components, there are only very few components that you need to actually understand. So I'll zoom in a little bit just to show you what components we will be focusing on today. So what we are focusing on today will be a register. PC is a register. Instruction register is a register. The flags register is a register. So we have a few registers, okay? And then inside this register bank, guess what? You have registers too. You got one, two, three, four registers. Okay. We got, let's see. Okay, we have four ABCD registers. We have the program counter as a register. We have instruction register. We have the flags register, and then we have the microcode pointer, which is also a register. There's a total of 8 registers in this entire processor. Okay, so it's not that many. There are also components called a multiplexer. This is a multiplexer. The job of a multiplexer is a railroad switch. Does everybody know what a railroad switch is? Okay, I see some nods, okay, but not everybody. Okay, so I'm gonna look it up so that you guys understand what a railroad switch is and and why we need that kind of device. So we'll go ahead and just kind of take a quick detour to understand what is a switch. So rail, road, switch, Thomas, train. Okay, and we'll look up images. There we go. Okay, this is a that's a good representation. So let's head out to Amazon. As long as I don't click buy now, I'm safe. Okay, so just make sure I don't click here. This is a railroad switch. Okay, so for this explanation, We'll make sure that the switch itself is directional. Okay. So in this case, it's a two input, one output kind of device. So you can see that there are two inputs here, and there's only one output. Okay. So this is not exactly a switch because you cannot really control it. Okay. So you can actually get ones that are switched. So we can now say, let's look for switched. Or just look up a picture where one is actually switched. This one is. Okay, see this little lever here? This lever is controlled by something, in the tower. So it can flip like this to this. Okay, so you can go one way or the other. So we'll also imagine the trains are going in one direction. So they're only going from your right to your left. Okay, that's a multiplexer. A multiplexer is essentially a device where there are multiple inputs. It will hold all the inputs except for one, and then that one becomes the output. Is that okay? It's a traffic controller. Okay. Okay. You have multiple inputs. It will say, hey, you, and you. Okay. You guys cannot go through, but you, on the other hand, now you can go through. Is that okay? Do we understand the purpose of a switch or multiplexer? Yep. It doesn't store anything. All it does is to control whether the path is open or not. Okay, so that's my explanation, but there's also an explanation that is built into LogicSim. So inside LogicSim, you can go to help and then go to users. Oh, nope, you go to library reference. Okay, so we have talked about the library reference before. So now I just need to bring this into your view. This is the library reference. All the multiplexers and demultiplexers are listed under plexers, and this is the multiplexer, okay? And it is fully explained. Copy an input on the west edge, which is your left-hand side, onto the input on the east edge, which is your right-hand side. Which of the input to copy is specified via the current value received through the input on the south edge? So that would be the one with a gray dot on top, okay? It is called the select pin. I find it useful to think of a multiplexer as as analogous to a railroad switch controlled by the select input, okay? And then it goes in and explain a whole lot more. So I think it'll be helpful if we just kind of focus on this one device and explain, all the little ins and outs of a multiplexer. So now I put a multiplexer here, okay? So if I select the multiplexer, it will show me all the things that I can control with a component like this. This one, facing, it's just, rotating the multiplexer so that it looks good depending on, which way you want the output to point to. So it's not really that important. Select location, you can either put the select location, at the bottom, or you can put it on top. So once again, it's just appearance. Okay, it's not really that important. But the other ones are kind of important. This one only has one single select bit. So when you only have one bit to specify which input, how many inputs can I select using only one bit? Only two, right? So let's skip all the way to three, okay? If I have three select bits, up to how many inputs can I select? Not six. Nope. Eight. That is correct. Because eight is 2 to the power of 3. Okay? So the way we look at multiple select bit is like this. Okay? So what you can do is to think about two input and only one select. Okay? So let's just say this is the only device we have. Okay? We do not have multi-select. So what you do is now you can say, okay, what if I have two of these? Okay? And then I run these two wires together. So now, when you say 0, 0, okay, then let's see. No, I need a I need another one. Sorry. No, I need three of them to get this to work. But the idea is you have a tree of multiplexers. So this is another multiplexer. It takes the output of one, takes the output of the other one, and this is another select. So the select of this one is going to be same as this one here. The select of this one is its own. Okay, so think about this configuration. If I say 1, 0, which one of the four inputs is going to become the actual output of the last multiplexer? So we'll say this is input 0, this is input 1, this is input 0, input 1, and once again this is input 0, this is input 1. And we'll name the four inputs, okay? We'll name this one input 0, input 1, input 2, and input 3. So if this is a 1, 0, which input becomes the actual output? It'll be, okay, so let's find out, okay? So the way we figure this out is this 0, okay? This 0 is getting this to connect to the output. So we know it's coming from here, okay? And then this one, which is fed to this one here, but guess what? This is useless because I'm not paying attention to this input of the final stage multiplexer. But I am I'm paying attention to this output here. This one is also connected to this one over here, which means that this one is now connected here. So input one is now actually connected to the output. What if I use 1, 1? Yep, it would be input 3 that's connected to the output. So that means if there's no way to make a multi-select bit multiplexer, I can just use the basic one and stack it in order to make it larger and larger. So if I want to have a 3 input one, it will look like this, okay? I will have 4 first stage multiplexers. I will have 2 second stage multiplexers, and then I'll have one third stage multiplexer. So the way the connection would be kind of like this. These two will be hooked up like this. These two will be hooked up like this. And then I have exactly 8 possible inputs. And then using that particular method, this is one select, which is shared with all of the other ones on the same stage. Okay. The second stage, same thing. Okay. This will be the other selected, and it will be shared with everything in the second stage. The third stage has its own input. So now, with 3 bits for selection, I can now select any one of the 8 possible inputs to connect to the last stage of the output. Is that okay? All right. So that's essentially how a multi-select bit multiplexer works internally. Fortunately, you don't have to do this kind of stacking because all you have to do is to now to say, oh, I don't want to just have one select bit. I want to have 3 select bits. Then the multiplexer now becomes an 8 input multiplexer. In other words, what you see on the projector is really the same thing as what you see on the whiteboard, except we are hiding all the details within the dotted lines. You just see the final interface. Okay. So are we doing okay so far in terms of what the select bits are doing? Okay. So we'll go to just using 2 select bits because 3 is a little bit too many. So we go back to 2. Now we have data bits. So data bits is not really surprising because all it does is to control from the input perspective how many bits should the input be. So when you hook it up like this, it complains because this is a single input bit, input pin. So all you have to do is to change this to 3 input and it's happy again. So now what we can do is to just kind of duplicate this a few times to simulate the 4 possible inputs. Okay, so here's the second one. Here's my third one, and I can just kind of play with the input pins to change the states. Okay, so we got this. Okay, the output it would also be 3-bit wide in this case. Okay, so we will give it a 3-bit output pin, like so. There we go. Okay, and then we also need a 2-bit input for the select. So the input that is actually doing the selecting has a gray dot notation. So that makes it easy to differentiate, the two pins, on the bottom side. So now you ask, what is that pin over here? Okay, because we have all the input, we have the output, we have the selection, okay, which selects which input connects to the output. What about this thing over here? That is, let me see. It is not the selection. The selection is the one with the gray dot. The one without the gray dot is enable. Okay. So that is the enable. Okay. So this pin here is letting you to select here. So right now it is a yes. So this include enable being a yes is why we have an extra pin over here. Okay. That's the enable pin. So we're going to go like, okay, if there's an enable pin, we want to be able to control that too. So now we hook up another input pin to the control pin. So you can probably guess that a 0 means disable, okay? So a 0 here connected to the enable pin is saying, okay, the multiplexer is disabled, which means none of the input is going to the output. Is that okay? And that's why the output is reading quote unquote XXX because X means it is floating. I have no idea what the value really is because nobody specifies the value of that location. But this is where things get a little bit tricky because when you look at the multiplexer, we explained all of the attributes except for one. We explained the phasing, okay, that's just rotational stuff, just for the looks. We explained the select location, which is basically saying um, on is the gray dot on the top or at the bottom, okay? Once again, it's just the appearance, it doesn't change the behavior. We explained the number of select bits, okay? So two select bits allow us to have four inputs, okay? We got that. Data bits, okay? Each input and the single output, they are now 3-bit wide, okay? We explained the last one, which is does it include enable? Can I enable and then disable it? Yes, and therefore we have an extra port for the enable. What we have not explained is disabled output, okay? Which is basically saying if the multiplexer is disabled, what should be the output? Which is exactly what we are seeing right now, okay? This is floating. But in addition to floating, you can also specify 0, okay? And that's why, when you specify 0, the inputs can be whatever, okay? So let me just kind of flip the inputs so they are non-zeros. So we'll go ahead and flip this one to be 0, 1, 0. This is 1, 1, 0. This is 1, 0, 0, 1, 1. And the last one is 1, 0, 1. Okay. And you can see the output remains to be 0, 0, 0 because the multiplexer is 1, disabled. 2, we configure it so that the disabled output is 0. Is that okay? But you can configure it to be floating. Okay, so if I go back and reselect the multiplexer, and this time I change the disabled output to floating, then the output becomes XXX because the device simply does not specify what the output is supposed to be, and that's why it reads as XXX here. What if I turn on the device? Okay, so now we will go ahead and turn on the device. But before I do, let me tell you what I want the output to be, and you guys tell me how I should specify the select bits. Okay, I want the output to be 0, 1, 1. How should I specify the select bits? 1, 0. You are correct. Okay, so let's try that out. Okay, so we change the select bit to 1, 0, which is 2 in decimal, and now we enable the multiplexer, and it is now selecting input 2, which is input 1, 0, to connect to the output. What if you're dealing with a multiplexer with so many input pins you cannot count? Okay, you can actually use a mouse pointer and just hover over input 1, input 2, input 3, and that's input 0. Is that okay? All right. Um, okay. So the last thing that you probably need to know is the register, okay? So there is an official explanation of the register. The register is inside memory library, and then you just go to register, and it would explain, all the pins related to a register. Most of the pins I have explained already, okay? So I'm just gonna go through a quick review with one little caveat, okay? So we'll talk about that one single caveat. D pin is the same as the D pin when I explain the register, as the first part of the lecture. Q pin is the same as the Q pin, the output of the register, as I explained it. Enable is referring to this pin over here, which does the same thing as enable. The clock pin does not spell CLK. Instead, it looks like a little triangle, which is at the bottom. That is a clock pin. The one caveat, okay, that is opposite to the way that I explained it is 0. Okay, so this little 0 here is a reset pin. The difference between this reset pin and the way I explained the reset pin earlier is this one is you need this pin to be a 1 to reset the content of the register all the way back to 0. So the polarity of the reset pin is opposite to the one that I explained earlier. But that is fully explained, okay, within the help explanation itself. So if you scroll down, it will tell you Um, let's see here. South edge labeled 0, input bit with 0. This is asynchronous reset. When 0 or undefined, the input has no effect, which is opposite to the one that I explained earlier in class. As long as it is 1, the register's value is pinned to 0, which means you can do all kinds of stuff with all the other pins. It doesn't matter. The output of the register remains to be 0. One more thing, okay, that you need is you can actually change the value of a register by clicking it. So we'll go to memory, go to register, stash it here. So if you want to change the value of a register, one thing you can do is simply to click on the number, then you can input the hexadecimal number corresponding to the pattern that you want, okay? So if I want this to be 7E, you just type 7E, and now 7E becomes the content of this register. So you can basically inject a value into a register by simply clicking it and typing over it. That you cannot really do with a real register, but inside a simulator, you can do it. So that's pretty much everything you need for tonight's lab. Okay, so we are transitioning slowly, okay, from the calculation and the representation of value to the components that are inside the processor. So once we explain all the components inside the processor, then we'll actually understand the processor and how instructions execute. Once I explain how instructions execute, then we'll look into how do we use those really simplistic instructions to do complicated things like recursive algorithms and so on and so forth. And the whole processor only has 256 bytes of RAM. You would think, well, we probably will have some little toy program to run, but nothing more than that. Well, I can tell you that we can implement the Tower of Hanoi with only 256 bytes of RAM with this processor. Okay, so we'll be doing some fun projects, in for the rest of this semester. You do need to know the access code of your lab tonight. Okay, so let me go back and give you the access code. I still have to reset the time, but by the time you get to the lab, it should be reset. So the access code is edgy, and I will set up the time. By the time you get there, it will have the time. Test.